Number 13 says, if x squared plus y cubed is x cubed times y squared, then what is dy dx? In other words, what's the derivative of y with respect to x? If you ever get a question like this where y is not isolated and there doesn't seem to be any easy way to isolate y, typically these problems can be handled using a technique called implicit differentiation. And what that means is we can find the derivative with respect to x of both sides of the equation, and using the chain rule should be able to find a dy dx within that next statement. So let's take the original equation, x squared plus y cubed equals x cubed times y squared, and start to differentiate both of these sides with respect to x. On the left-hand side, we'll start by differentiating x squared with respect to x, and we get 2x. This is using the power rule. What's a little bit harder, I think, to remember is how to find the derivative of an expression involving y when you're differentiating with respect to x. And to do that, you actually have to use the chain rule. Now, we kind of did use the chain rule with the x squared, but the inside function is x, and the derivative of x with respect to x is 1. So really, there's like a times 1 here that you wouldn't normally write. But with y, when we find the derivative of y with respect to x, dy dx is not 1. So when we differentiate this, we're going to use the power rule, 3y squared, but then due to the chain rule, we need to find the derivative of y with respect to x. And that's where that dy dx is going to come from. Then on the right-hand side, we'll have to use the product rule. The product rule has us multiply the first function, in this case, x cubed. The derivative of that is 3x squared times the second function plus the original first function times the derivative of the second, which through the power rule and the chain rule is 2y times the derivative of y with respect to x. Now our goal here is to find dy dx, so we're going to have to algebraically isolate that from everything else. To do that, we want to bring all the terms that have a dy dx, and there's only two of them, over to one side, and bring all the other terms to the other side. So the 3y squared dy dx is already on the left-hand side, but let's bring that x cubed times 2y over there as well. So I've got that 3y squared dy dx minus x cubed times 2y. I'm just going to rewrite that ever so slightly as 2 times x cubed y dy dx. And then the other two terms should be over on the right-hand side. The 3x squared y squared is already over there, but if we subtract 2x from both sides, we can get that other term over to the right-hand side. Next, we're going to factor out the dy dx, which is what we're actually trying to find, as a GCF, or a greatest common factor, from the left-hand side, kind of like using the distributive property in reverse. So I'm going to factor that dy dx out of each term, leaving me with this expression. For now, I'm going to leave that right-hand side alone. Finally, to get the dy dx by itself, I need to divide both sides of the equation by this entire expression here, the 3y squared minus 2x cubed y. So if I divide both sides by that expression, I'll have the dy dx by itself, and on the right-hand side, I'll have 3x squared y squared minus 2x all over what I'm dividing by, which is 3y squared minus 2x cubed y, and we can see that our answer is C.